2.1 Exponential Functions. Part 1. Graphing and Solving Exponential Functions. Southwestern College, Professor Maria Olivas. Section 2.1 Exponential Functions. Objectives: graphing and solving exponential functions, and graphing and solving exponential functions of the natural base e. 1. What is an exponential function? Definition: an exponential function is a function of the form f of x equals a sub 0 times a raised to the x power, where a is greater than 0 and a cannot equal 1. I've underlined the words exponential function. I've drawn an arrow pointing at a sub 0, and I've labeled that as our coefficient. I'm drawing an arrow now at a, and I've underlined it twice, and I'm writing this as our base. And then the x, I've drawn an arrow pointing to the x, and I'm labeling that as our exponent. The key part to remember is that your variable is going to be in the exponent. I'm circling a greater than 0 and a cannot equal 1 because that's a very important part of an exponential function. So you always have to make sure you double check these things if you are checking to see if there is something that could be potentially an exponential function. 2. Graphing exponential functions. Example 1. Graph y equals 2 raised to the x power. I'm going to rewrite this so you can see the coefficient in this example. I'm going to rewrite it as f of x equals 1 times, open up a set of parentheses, 2, close the parentheses, and then raised to the x power. So here you can see that the 1 represents the coefficient. I'm going to write that down. Our coefficient in this problem is equal to 1. Our base in this problem is going to be equal to 2. And the exponent is going to be the x. And whenever you have an exponential function, of course, you are going to have your variable in the exponent part. So now that I've written here underneath base equals 2, I wrote a equals 2, and I'm pointing up at our definition where we had the a raised to the x power, so you can see that that's what this represents in that base part. I am going to draw a 2-column table in order to come up with some ordered pairs to help me sketch the graph of this function. The first column is going to represent our x values, which is -2, -1, 0, 1, and 2, and our second column is going to represent our y values. In order to come up with those y values, I'm going to show the work right here on the right-hand side. So let's start off with f of -2 is equal to 2 raised to the -2 power, which is equal to 1 over 2 squared, which is equal to 1/4. So that for that first value, it's going to be -2, 1/4. f of -1 is equal to 2 raised to the -1 power, which is equal to 1 over 2 to the first, which equals 1/2. f of 0 is equal to 2 raised to the 0 power, which is just 1. f of 1 is equal to 2 to the first, which is 2. And f of 2 is going to be the same thing as 2 raised to the second, which is equal to 4. And those are our ordered pairs. I am going to go ahead and lasso the 2-column chart and move it to the left-hand side and shrink it. I'm also going to lasso the work I just did for finding my y values. I'm going to also shrink it and move it to the left. I'm also going to move a few more things over to the left to give me more space. I'm going to move my function that I rewrote as f of x equals 1 times 2 raised to the x to the left, and I'm going to move where it says coefficient equals 1, base equals 2, and a equals 2 to the left. Now I'm going to draw my coordinate plane. I've drawn a vertical axis for my y-axis, and I've drawn a horizontal axis for my x-axis. I'm going to go ahead and draw tick marks on the x-axis. I'm going to draw tick marks ranging from, it's going to be from -2 to 2, separated by a scale of 1. On the y-axis, I'm going to draw from 0 to 4, separated by a scale of 1. So now I can go ahead and plot my points. I'm going to show some values here on the y-axis for the 1/2 mark and the 1/4 mark, so I can plot my ordered pairs. First point I'm plotting is -2, 1/4, then -1, 1/2. Next is 0, 1. Next is 1, 2, and then 2, 4. I'm going to go ahead and draw the curve that goes through these points, extend it all the way to the ends of my coordinate plane, and draw arrows on the ends. I'm going to label this with the equation y equals 2 raised to the x power, and I'm going to label each one of my points with its corresponding ordered pair. Now you are going to see a dotted red line appear over the x-axis. This represents the horizontal asymptote y equals 0. You can find the horizontal asymptote by identifying the constant being added to the exponential function. In our function y equals 2 raised to the x power, there is an imaginary plus 0 being added, therefore representing the equation y equals 0. Now we weren't asked to graph the horizontal asymptote for this particular problem, but I thought it might be useful to mention it, so that way in the future, if you do need to be aware of the horizontal asymptote, you know how to find it and you know how to graph it. Before we finish up this problem, I also want to write down the domain and range. Even though we weren't asked to find it, it's important to know how to find those things. The domain for this particular function is going to be the open interval from -infinity to infinity, or the set of all x, such that x is an element of the set of real numbers. When finding the range, it is helpful in knowing about any horizontal asymptotes, because that will affect the range. I've circled the function y equals 2 raised to the x power because remember there was a plus 0 at the end of that exponential function, so therefore there was a horizontal asymptote. This function cannot go below the x-axis, so the range is going to be the open interval from 0 to infinity, or the set of all y such that y is strictly greater than 0. Properties of y equal to a raised to the x power with a greater than 1. This represents exponential growth. 1. The domain. For the domain of these type of functions, the domain is going to be the set of all real numbers, or the open interval from -infinity to infinity. I'm drawing a cloud around the y equals a raised to the x power, and the condition where it says a is strictly greater than 1. The range is going to be the open interval from 0 to infinity. And for number 2, our end behavior, we're going to look at the limits here. The limit as x approaches -infinity of a raised to the x power is going to be equal to 0. And the limit as x approaches positive infinity of a raised to the x power is going to be equal to infinity. So here we can see, if we look to the left-hand side where I've highlighted in yellow, what happens as x approaches -infinity. Our function gets closer and closer to the value of 0. And I've highlighted in green here what happens as x approaches positive infinity. As x approaches positive infinity, our function also approaches infinity. Normally, we never write that a limit is equal to infinity because it is not a specific value that it's approaching. But because we're talking about end behavior, for this time, we're going to leave it like this. We normally say a limit does not exist when it equals infinity. Our y-intercept here is at 0, 1. So I have circled it so you could see exactly where it's at, where it's crossing our y-axis. And we're going to just go ahead and label that. I'm going to have an arrow pointing towards it, and I'm going to write in y-intercept and double underline it. These are things you should be able to find or identify when you're graphing these functions. Example 2. Graph y equals 3 raised to the x power. I'm going to go ahead and copy the table of values that I used for our first example, and I'm just going to erase the y values. But I'm going to use the same x values that I had originally chosen for my 2-column table. X values were -2, -1, 0, and 1, and 2. So y is going to be equal to 3 raised to the negative 2, which equals 1 over 3 squared, which is 1/9. And then y equal to 3 raised to the negative 1 is equal to 1/3. Y equal to 3 raised to the 0 is equal to 1. Y equal to 3 raised to the first is equal to 3. And y equal to 3 squared is equal to 9. I'm going to go ahead and draw a coordinate plane right here on the right hand side of the screen. I'm going to start off by drawing the vertical axis, and then I will draw the horizontal axis. I'm going to also go ahead and draw some tick marks here. I'm going to start drawing the tick marks on the x-axis, and it's going to go from -2 to 2 by a scale of 1. I've gone ahead and I've tried to erase that page number so it's not showing up here on my coordinate plane. So that's what I'm trying to do right now. Okay, now we can draw the tick marks on the y-axis. I'm going to draw tick marks from 0 up to 9 by a scale of 1. I'm also going to draw some values in there to represent our 1/9 value and our 1/3 value. And now I'm going to plot the points. I've started by plotting the points -2, 1/9, -1, 1/3, 0, 1, 1, 3, and 2, 9. Now I'm drawing the curve to connect those points. I'm extending my curve all the way to the ends of the coordinate plane, and I'm drawing arrows on the end of my function. I'm going to go ahead and label the ordered pairs for each one of these points. So I started off labeling -2, 1/9, then -1, 1/3, then 0, 1, 1, 3, 2, 9, and I've labeled the equation of the function y equals 3 raised to the x power. I'm now circling the y-intercept, and I'm drawing an arrow at it, and I'm writing the word y-intercept, pointing at it, and I've underlined y-intercept. Example 3. Suppose you deposit $1,500 in an account that earns 3.5% annual interest. The value of the account after t years is given by the equation v equals 1,500 times 1.035 raised to the t power. I'm highlighting the $1,500 and the 3.5% annual interest, and I'm also highlighting the equation of our function, the v equals the 1,500 times the 1.035 raised to the t power. I'm also going to circle where it says t years. This is all key information. I've also circled the v in the equation. A, find the value of the account after 2 years, 10 years, and 20 years. So let's go ahead and do this. I'm going to write here v of 2 equals, we're going to substitute 2 for our t, 1,500 times 1.035 raised to the second power. So v of 2 is going to be equal to, well actually let's do this first on the calculator here. I'm going to go ahead and type in my function. I'm going to press that y equals button in the upper left hand corner, and I'm going to type in for y sub 1. Y sub 1 equals 1,500 times 1.035 raised So now that we to have the input our x function, power.
I'm going to go to second and table set. I'm going to have the table start at 2. Right now it says it's starting at -3, but I want it to start at 2 because I'm evaluating the function at 2. And then I'm going to go to second table, and my table pops up here with values for x on the left hand side and values for y on the right hand side, or y sub 1. At the very top of the table we see 2 and 1,606.8. If I scroll down, I see that it goes all the way up to 20. At the top of this, here at this table, I have x equal to 10 with y equal to 2,115.9, and at the bottom I have x equal to 20 and y equal to 2,984.7. So from looking at this table, I'm able to get the values that I need to evaluate my function. I can also go second quit and then click on, I'm going to go to vars, V-A-R-S. And here I'm going to scroll over to the right one spot, click on the y vars, and then click enter on the y1. Open up a set of parentheses and type in 2. And we get the value 1606.8375. Now let's go back to that vars button, that V-A-R-S button. Let's scroll over to the right to y vars and hit enter on y1. Open up a set of parentheses and type in 10 so we can evaluate this function at 10. And close our parentheses and press enter. And we get 2115.898141. Let's go back to vars, y vars, and y1 so we can evaluate our last value here. We have y1, open up a set of parentheses, 20, close the parentheses, enter, and we get 2,984.683295. So you can see there is more than one way that you can evaluate these functions on your graphing calculator so that we can get these values that we were looking for. Now, since it's a word problem we're working with and it is asking us to give a dollar amount, we're going to round to the nearest cent. V of 2 is equal to, I'm going to round this to 2 decimal places, $1,606.80. V of 10 is going to be equal to $2,115.90, and V of 20 is going to be equal to $2,984.70. These are actually all more like approximations because I am rounding to 2 decimal places. B, sketch a graph of this function from t equal to 0 to t equal to 20 years. I'm going to draw a coordinate plane here. This is going to represent my vertical axis, my y-axis, and here is my horizontal axis to represent my x-axis. I'm going to label them actually with my horizontal axis is going to be my t-axis, t for time in years, and my y-axis or my vertical axis is going to be v of t, which is representing the value of the account. I've gone ahead and drawn little tick marks here on the t-axis from 0 to 20, and they're drawn by a scale of 2. I've labeled them all in. And for the v of t, I'm going to go ahead and draw some tick marks on that axis as well. And we're going to scale those by 500. So we're going to go from 0 up to 3,000. I've circled t equal to 0 and t equal to 20 because I want to definitely include those values when I'm sketching my graph. So when I use my ordered pairs, I definitely want the values for t equals 0 and t equals 20. I've done a 2-column table for values of t and v of t. And under t, I've chosen the values 0 to 10 and 20. Values that I already happen to have. I already evaluated v of t for those values. V of t equal to 1,500 times 1.035 raised to the t power, but I'm going to find v of 0 because that's the only one I'm missing. So v of 0 is equal to 1,500 times 1.035 raised to the 0 power. So v of 0 is equal to 1,500 times 1, which is equal to 1,500. I've gone ahead and filled in all the values for v of t. So 0, 1,500, 2, 1,606.80, 10, 2,115.90, and 20, 2,985.70. I'm going to go ahead and plot these points. So I'm plotting down the point 0, 1,500, 2, 1,606.80, the next one 10, 2,115.90, And the last one, 20, 2985.70. I have drawn a curve connecting these points to represent my function. Now, because it only said sketch a graph of this function from t equal to 0 to t equal to 20 years, I am being very careful not to extend my function past those values of t. So there are no arrows on the ends of this function. It has like a start point on the left and an end point on the right. So it does have like a place where it stops. I have labeled each one of those ordered pairs. Each one of the points has been labeled with its corresponding ordered pair. So we are done with that. We have sketched our graph. We can see that this function is increasing from t equal to 0 to t equal to 20 years. So definitely the value here will increase within those 20 years time. Example 4, graph y equals 3 raised to the negative x power. So let's go ahead and start this problem off here. We're going to begin by writing this as f of x equals 1 times, open up a set of parentheses, 3, close the parentheses, raised to the negative x power. So now I'm going to write f of x equals 1 over 3 raised to the x power. And this is also the same as this equals 1/3 inside a set of parentheses, raised to the x power. I've highlighted the 1/3 inside the parentheses in yellow so that it stands out, so we can see that this value of a here is a value that is less than 1. I made a 2-column table with the values of x on the left-hand side and the values of f of x on the right-hand side. Under x, I have written the values -2, -1, 0, 1, and 2. So now we're going to evaluate the function for these values. F of -2 is equal to 3 raised to the negative times -2
Another way
power,
to evaluate
f
of -2 would be this way. F of -2 is equal to, open up a set of parentheses, 1/3, close the parentheses, raise to the -2 power, which is equal to 3 squared, which equals 9. So we have the ordered pair -2, 9. F of -1 is equal to 3 raised to the negative times -1 power, which is equal to 3 raised to the first, which is equal to 3. And f of 0 is equal to 3 raised to the -0 power, which is equal to 3 to the 0, which is 1. F of 1 is equal to 3 raised to the -1 power, which is equal to 1/3. F of 2 is equal to 3 raised to the -2 power, which is equal to 1 over 3 squared, which is equal to 1/9. I've also gone ahead and written down these y values under the f of x column so that I have the ordered pairs -2, 9, -1, 3, 0, 1, and 1, 1/3, and 2, 1/9. I've taken all that work, I've lassoed it, I've shrunken it a little bit and moved it slightly to the left-hand side so I have more space on the right to draw my coordinate plane. So now we're going to draw my coordinate plane here. I've drawn the vertical axis. I've drawn the horizontal axis. I'm going to begin by drawing the tick marks on the horizontal axis, our x-axis. They're going to go from -2 to 2 by a scale of 1. And on the y-axis, I'm going to go from 0 to 9 by a scale of 1. I've also drawn in the value for 1/3, and I can kind of estimate that 1/9 will be in between 0 and 1/3. So now I'm going to plot down these ordered pairs. We're going to plot down -2, 9, -1, 3, 0, 1, 1, 1/3, and 2, 1/9. I'm going to connect those ordered pairs, and I'm going to draw arrows on the ends of my curve here. I'm going to label each one of the points with its corresponding ordered pair. And I'm also going to label this function with its equation, f of x equals 3 raised to the -x power, or we could also use the equation y equals 1/3 raised to the x power if we wanted to. There is a horizontal asymptote here at y equal to 0 right on top of the x-axis, even though I did not
show it, you guys should be aware of it. And you guys should be aware also of the domain and range. The domain of this function is going to be all the reals, and the range is going to be the open interval from 0 to infinity. Properties of y equals a raised to the x, where a is less than 1.
I have drawn a cloud around the equation
y
equal to a to the x power and the inequality a is less than 1.
And I have highlighted the a is less than 1, drawn an arrow pointing up to the 1/3, and I've also highlighted the 1/3 in yellow in the problem that we just did. So here our a was equal to 1/3, which is less than 1. Or another way that we could write the same problem, we could also write it as y equal to a raised to the negative x power, where a is greater than 1. So it means the same thing. Both of these, whether it's written as y is equal to a to the x power, where a is less than 1, or y is equal to a raised to the negative x power, where a is greater than 1, these represent exponential decay problems or exponential decay functions. I am going to circle where it says y equals 3 raised to the negative x in the original problem, and I'm pointing an arrow at the 3 as the base, and I'm writing a equals 3. This is an example of the y equal to a raised to the negative x where a is greater than 1. I've also highlighted the words exponential decay. So here for domain, our domain here is going to be the open interval from negative infinity to infinity. Our range is going to be the open interval from 0 to infinity. And as for end behavior, we're going to look at the limit as x approaches negative infinity of f of x. This is going to be equal to infinity. Here, I'm going to highlight the left-hand side of the x-axis in blue, and I'm also going to highlight the left-hand side here of the function in blue. So as we are approaching negative infinity, or as x is approaching negative infinity, you can see that our function is going to go up towards infinity. The y values are going to get very large. And as for the limit as x approaches positive infinity of f of x, that's going to be equal to 0. Since I've already highlighted here in green the right-hand side of the x-axis and the function, you can see that as x goes to infinity, the function is getting closer and closer and closer to 0. The number e is an irrational number named after the famous mathematician Leonhard Euler, who lived from 1707 to 1783. It is a special number in many ways and pops up in many places. The definition of e gets complicated, so for now, we're just going to say that e is equal to the limit as x approaches infinity of, open up a set of parentheses, 1 plus 1 over x, close the parentheses, raised to the x power. And this is approximately equal to 2.718. Example 5. Graph f of x equals e raised to the x power and g of x equals e raised to the negative x power. So I have rewritten down the function f of x equals e raised to the x. I am drawing a 2-column table. The left-hand side is going to represent my values of x. The right-hand side is going to represent my values of y. I have also copied this table and pasted it right under the function g of x equals e raised to the negative x, because I'm going to come up with a table of values for that function as well. Under the x column, I wrote down the values -2, -1, 0, 1, and 2. And then for our y column, or our f of x column, we're going to get for our first function, f of x, e raised to the -2 power is equal to 1 over e raised to the second, e raised to the -1 power is equal to 1 over e raised to the 0 is equal to 1, e raised to the first is equal to e, and e raised to the second is just e to the second. I'm going to write down approximations so that I can actually sketch this. 1 over e squared is approximately 0.135. 1 over e is approximately 0.368. E is going to be approximately 2.718. And e squared is approximately 7.389. So that should be enough in order for me to come up with a sketch for that graph. Now for g of x is equal to e raised to the negative x, for the x values, I'm going to use the same x values, -2, -1, 0, 1, and 2. For g of x, let's find g of -2 first. G of -2 is equal to e raised to the negative times -2 power, which is equal to e squared. So we're going to have -2 comma e squared. For the -1, that's just going to give me e. For x equal to 0, we're going to get 1. For x equal to 1, we're going to get e to the -1, which is equal to 1 over e. And for x equal to 2, we're going to get e to the -2 power, which is equal to 1 over e squared. Now, for the approximations for these, e squared is approximately equal to 7.389. E is approximately 2.718. E to the -1, which is equal to 1 over e, is approximately equal to 0.368, and 1 over e squared is approximately 0.135. I have taken all of the work I did there and all of the tables, and I have lassoed it, shrunk it, and moved it slightly to the left so that I have a little bit more space so that I can draw my coordinate plane to the right-hand side. I've drawn my coordinate plane with my x and y axis. I have drawn tick marks on the x-axis that go from -2 to 2 by a scale of 1. I'm drawing tick marks here for my y-axis, and these tick marks go from 0 to 8 by a scale of 1. Now I'm going to go ahead and plot my points. I'm going to go ahead and start by plotting the point -2 comma e raised to the -2, which was approximately 0.135, -1 comma e raised to the -1, which was approximately 0.368, 0, 1, 1 comma e, and e is approximately 2.718, and 2 comma e squared, which was approximately 7.389. I have drawn my points. I have connected them with a curve, and I have extended my curve to the ends of my coordinate plane, and I have drawn arrows on the ends of that coordinate plane. I have labeled that function with its equation f of x equals e raised to the x, and I am labeling each one of my points with its corresponding ordered pair. Now we're going to go ahead and plot the points for g of x is equal to e raised to the -x power. Let's start off with -2 comma e squared, which is approximately 7.389. Then -1 comma e, which is approximately 2.718. 0 comma 1. 1 comma e raised to the -1, which was approximately 0.368. 2 comma e raised to the -2, which was approximately 0.135. I have drawn a curve going through those points. I have extended the curve to the ends of my coordinate plane. I have drawn arrows on the ends of my function. I have labeled that function with its equation g of x equals e raised to the -x, and I have labeled each one of my points with its corresponding ordered pair. So you can see by looking at this coordinate plane that these two functions are symmetrical about the y-axis. They're like the mirror image of each other across the y-axis. Let's move on to example number 6. Example 6. The formula a equals p times e raised to the rt power is used to compute the amount of money in an account t years after an initial investment of p dollars, earning at an interest rate of r, compounded continuously. If you invest $10,000 in an account that earns 4% interest compounded continuously, how much money will be in the account after 12 years? How many years would it take for the account to have a value of at least $24,000? Use your calculator to help you solve this. So to begin solving this problem, I'm going to go back and highlight and underline key information that is given to us in this word problem. Let's begin by highlighting the formula a equals p times e raised to the rt power, because that is a key formula that we're going to need to solve this. I'm going to choose to highlight this in yellow. Let's also highlight the part that says compounded continuously, because this part is telling us what type of interest problem this is. There are different types of interest problems that can be compounded differently. I'm going to underline the part that says if you invest $10,000 in an account that earns 4% interest compounded continuously, how much money will be in the account after 12 years? I'm going to put a number 1 next to it, and I'm going to start writing here after the number 1 that I'm writing underneath, A of 12, because this is actually like the first question that's being asked of us. So let's go ahead and set this up. A of 12 is equal to 10,000 times E raised to the 0.04 times 12 for the 12 years. So here we're finding A of 12, which represents how much money will be in the account after 12 years. Put this into the calculator, this is going to be approximately equal to $16,160.74. So part 2, the second question here says, how many years would it take for the account to have a value of at least $24,000? And use your calculator to help you solve this. I just underlined that sentence. That's the second question we're being asked. So I'm going to kind of label this work here as, our second part, or our part 2 question that we're being asked. I've highlighted in green the A in the formula A equals P times E raised to the RT, and I've highlighted the $24,000 in green as well, because that is the amount that we're looking for. We're looking for how many years it'll take, so we've got to replace the A with the 24,000. So I've written down the formula A equals P times E raised to the RT, highlighted the A in green, and instead of A, I've written 24,000. I've highlighted the P in blue, and I've highlighted the $10,000 in blue, which represents the initial investment of P dollars. So it's going to be 24,000 equals 10,000 times E raised to the, here we're going to have to raise it to the rate times the time. So our rate is going to continue to be that 0.04, which represents the 4%. And we don't know the time, so we're just going to put times t after that 0.04. I drew an arrow pointing at the t, and it's here I wrote after the arrow find t, because that's what we're being asked to find. We're being asked to find how many years would it take. So now I'm dividing both sides of my equation in order to isolate that e, which has the t in the variable. I'm dividing by 10,000 to both sides. 24,000 divided by 10,000 is going to be equal to 2.4. So I drew an arrow here pointing to the right, and I rewrote this equation as e raised to the 0.04 t power is equal to 2.4. I drew another arrow here pointing to the right, and I said let's use your GC, which represents use your graphing calculator. So let's switch to our graphing calculators. You're going to want to press the y equals button, which is the button in the upper left-hand corner. And then for y sub 1, our first equation, we're going to want to type in y sub 1 equals e raised to the 0.04 x power. X is going to represent t in this case. So let's go ahead and go second e and then raised to the 0.04 x power, and then press the down arrow key, and we're going to press 2.4 for y sub 2 equals 2.4. We're going to adjust the window a little bit here so we can see our point of intersection, because that's what we're looking for. Our x min is going to be -1, our x max is 30, the x scale is 1, y min is -3, y max is 7, and the y scale is 1. And if we press graph, we're going to see a graph where we see the intersection of two functions. The two functions we see here are y sub 1 is equal to e raised to the 0.04 x power, which is the blue curve, and y sub 2, which is equal to 2.4, and that's going to represent the red horizontal line here. So I can see that it's focused here mainly on quadrant 1, where the intersection is at. Now, in order to find that point of intersection, we're going to need to calculate that intersection. So we're going to want to go and press second and then the trace button, or we want that calculate feature that's above the trace button. So let's go ahead and do that. We're going to go to second and then calculate. We want number 5 for intersect. Now we're going to press enter on one curve, enter on the other curve, and then it says intersection x is equal to 21.886718 and y is equal to 2.4. So that's the intersection we wanted. We wanted that x value. the x value represents our time in years. Another option that we have is to go second table and to look at the table here. We have the table feature. We can scroll down and we see here between the values where x is equal to 21 and 22 that y sub 1 and y sub 2, they're almost equal to each other here. We've got the two values here. When x is equal to 21, y sub 1 is equal to 2.3164. And when x is equal to 22, y sub 1 is equal to 2.4109. And this demonstrates that in between those two values, there's going to be a value that is going to match up exactly with our 2.4 value for y sub 2, where these will be equal to each other. So I know my answer has to be an x value that's going to be in between x equal to 21 and x equal to 22, because that's what we're looking for. We're looking to see when our y sub 1 value is going to be equal to y sub 2. Let's go ahead and find this answer another way. Let's go ahead and press second quit to get out of that table feature. So another option that we have is we can use the natural log. So if we go ahead and take the natural log of 2.4 and press enter, we're going to get this value of 0.875468737. And if we take that answer and we divide it by 0.04, we're going to get 21.88671843, which is our answer there. So this is another option. We solve that equation that we had set up by using a natural logarithm, we can find it. So our answer here is going to be t is approximately equal to 21.886. Now, because it was talking about years, I'm going to round up to the next whole year, and I'm going to say this is about 22 years. Okay, so now that we finished answering the two parts or the two questions that were given to us in this problem, let's go ahead and box in our answers. Let's begin by boxing in the answer to our first part of the problem. How much money will be in the account after 12 years? So that was the $16,160.74. And then let's box in the second part, where I rounded it up to about 22 years, but I'm also going to box in the exact answer here, where it said t was approximately 21.886 years.